So it's a great pleasure and honor to be here today and give this presentation, in particular considering that the chair of the session is John Tanner. So thanks, Derek, for the invitation. So we heard about double diffusion encoding experiments yesterday in the talk by Joram Cohen, who was presenting results on an NMR spectrometer. We will hear more about experiments applied on preclinical scanner by Noam Shemish in the next presentation. So this is why I will focus on experiments on whole body MR system. And I will also take a somehow historical perspective, let's say, starting with our first attempts involving vegetables and tissue samples up to more recent results obtained in the human brain in vivo. So a short reminder, what is a double diffusion encoding? So it's just a, let's say maybe one of the simplest extension of the conventional Galtana experiment, just applying two diffusion encoding periods in the single experiment, one after the other, prior to the data acquisition. So this means that the diffusion-induced signal attenuation of our acquired MR signal depends on the combined effect of both diffusion encodings, and that means that there may interaction effects depending on the path of the spins during the experiment. And there are two important additional degrees of freedom compared to the normal single diffusion encoding experiment: the mixing time between the two diffusion encodings and the relative angle between the two gradients directions. And these two parameters may have a significant impact on the signal amplitude we acquire depending on the microstructural parameters of the sample, and they may emphasize different of these parameters. So this is why this approach is quite interesting and has found several groups that are doing research on it. So unfortunately, there are several names for this approach, for this double diffusion encoding in the literature, the most prominent being double PFG, double PGSE, double scattering, or double wave vector. So this is more or less all the same. So, and just recently, the community agreed on using the term double diffusion encoding. So please be not too sad if I may fall back into the double wave vector term we have been using in our lab for several years. So I will start with a short motivation addressing a few of the drawbacks of diffusion tensor imaging, now repeat the basic principles of double diffusion encoding, including the two mixing time regimes, mention some of the pitfalls we faced when starting with such experiments in our whole body scanner, before then presenting experiments targeting the compartment size and the microscopic diffusion anisotropy in the human brain. So our interest in double diffusion encoding was triggered by a diffusion tensor imaging study that showed reduced values for the fractional anisotropy in the brain of a group of volunteers having persistent developmental stuttering. So the interpretation of these findings may be straightforward. So because you usually assume that the axons provide the major contribution to the MA, you could just argue, okay, this could just represent a loss of axons, a loss of fiber density in the affected regions here that would explain the reduced value for the FA. But that's not the only, that's just one of the potential explanations. It could also be that there are more fibers, more axons in that region, that they have a different orientation distribution, because the fractional anisotropy also depends on the orientation distribution. In this particular case, you may have good reasons why this interpretation may be more closer to reality. But what about this example? Let's say a normal volunteer. You have regions with a high FA in white matter, but there are also regions in white matter where the FA is reduced. So is this just crossing fibers and normal, let's say, or is there already some axonal loss, some loss of fibers involved? So this is a question diffusion tensor imaging cannot answer. So looking for solution to this problem, we were stumbling across two papers. So one is, mentioned that before, the paper of Corey. They proposed a double diffusion encoding experiment to investigate spin transport processes. And in particular, they wanted to investigate pore leakage. But their paper, they also noted that this method could be used to measure the pore or compartment eccentricity. So that means to distinguish spherical cells, pore compartments, from eccentric or elongated cells, pore or compartments. And this was exactly the problem we were facing. So the other paper is a paper by Partha Mitra. He was considering experiments with multiple diffusion encodings more general and also in more detail. So he could confirm that for long mixing times between the two diffusion weightings, there is a W-shaped signal modulation. You have seen that before in the previous talk, that occurs for eccentric cells only, but not for spherical cells. So this was also the idea of Corey in their paper. But Mitra also found another interesting effect that's occurring at short mixing time. So in the presence of restrictions, there's a bell-shaped signal modulation, again with the angle between the two diffusion weightings, and the amplitude of this modulation that increases with the cell or pore size, but is independent of the particular shape. So we have two different effects that can be observed or are added to the double diffusion encoding experiment. So one is this anisotropy effect, let's say at long mixing time, a signal difference between parallel, antiparallel, and orthogonal diffusion weightings that reflects eccentricity and could be used to detect diffusion anisotropy. And the other one occurring at short mixing time, a signal difference between parallel and antiparallel diffusion directions that is a fingerprint of restriction and could be used to estimate compartment or cell or pore sizes. So while we were more keen on this type of experiment, we decided to start with this approach at short mixing times because we expected the signal modulations to be larger and thus the modulation to be more easy to detect on a whole body MR system with a very limited gradient amplitudes available. And furthermore, we decided to go or to start with vegetables because the pores are larger, so we further expected that the signal modulation is really detectable on the whole body MR system. So we became quite good customers of our local supermarket who really has a fine selection of MR phantoms available. So this is a vegetarian corner, let's say. So we found radish to be a quite good phantom. So some people say it's celery, but don't believe that. So for some experiments, radish is also quite nice. And we were looking at what we called the decay ratio, because according to the paper of Mitra, the signal decay compared to the non-diffusion weighted case should be 3 times as high for the signal minimum here than for the signal maximum here. And this was where radish was quite successful. So for short diffusion times, well, the ratio was something like 1.05, but if we increase the diffusion time, we could get quite large factors like 2.8 and even much below 3. So this was now data too good to be true, let's say. So we had a more detailed look at the angular modulation. So what happens if we vary the angle in more detail in the smaller steps between the two diffusion weightings? And then we found that we saw something like the bell shape, but also an extra peak signal here at the signal maximum. So this was not really to be there. So this was an artifact. So we became aware of several problems that were present in our experiment with a simple approach. Let's say the most important being cross terms with field inhomogeneity. So with the diffusion weighting that most likely caused this unusually high decay factors we observed here, and this extra peak, this was just a stimulated echo that was just occurring for certain relative orientations of the two diffusion weightings. So rather than using this schematic simple approach, we had to use something that looks much more difficult. So a pulse sequence that is inherently cross-term compensated for the two diffusion weightings with a spoiler scheme that does not induce cross terms, but nevertheless suppresses all the unwanted signals you may occur, in particular the stimulated echoes. So with this pulse sequence, we went to our favorite phantoms, water, and there we would not expect any signal modulation, and we see the modulation is absent, so it's a quite straight line. So this is what you expect, because in the water there are no restrictions. So this seems to indicate that there are no systematic signal variations anymore left in our data. For water between beads, where there is some restrictions or hindrance for the diffusion, we could see now the signal modulation, and also increased with the B value, with the strength of the diffusion weighting, which is really what you would expect. And for the tissue sample, we had pig spinal cord. We could also see the bell-shaped signal modulation, a bit more noisy, but nevertheless it seems to be there. We checked whether this could really be the effect we were looking for. By increasing the mixing time, you would expect that these modulations just occur for short mixing time. So when increasing the mixing time, the modulation should be reduced. This is particularly obvious here for the spinal cord sample. It disappears for longer mixing times. For a radish, that's not so pronounced because the pores are much larger. So this made us very proud, let's say, that this is really the effect we were looking for. And we became more brave and went to the human brain in vivo. So we started with the pyramidal tracts for several reasons. So first, it's not close to the ventricles or not too close to the ventricles, which means that ringing artifacts and fluids in the ventricles or so are minimized. It has a high signal amplitude if you apply the diffusion weightings perpendicular to the pyramidal tracts. And there were histological data available from the literature about the typical cell sizes in this region. So, and our data again showed a signal difference between the parallel and anti-parallel diffusion orientations as expected. We double-checked with our fluid phantom with the same acquisition protocol. You see there's nothing, there are no restrictions. And we also again checked with the mixing time, and you could see for the longer mixing time the effect also disappeared. So this is really much evidence that this is really the effect we were looking for. So based on these data, we estimated roughly, let's say, the compartment sizes that would give such a signal modulation. Depending on the model we were using, we got mean pore or mean cell diameters or mean compartment sizes, let's say, between 5 micrometer and 30 micrometer. So this is now really too big, let's say, for the normal point of view, let's say, because if you have a look at the histological data, you see, of course, that most of the axons in the pyramidal tracts are very small. But you have to consider that here we measure something where the volume fraction plays an important role, and the few axons here that have a large diameter, they provide a much larger volume, and that means also a much larger signal. So if you take into account the volume these axons provide, then the distribution is much more flat, let's say, and if you then take the mean value, you end up with something like 8 micrometer as a diameter, so which was well in the range we have found. More recently, Peter Bazza's group developed a more extended model and more extended acquisition for this kind of experiment. So they used the multiple correlation function formulas, and Evan has introduced just to model the data, and they considered a microstructure model considering restricted and unrestricted diffusion, and could get quite reasonable estimations of the average axonal diameter and the axonal volume fraction in the human corpus callosum in vivo. So quite promising, but originally we wanted to go for the anisotropy stuff. So let's come back to this. So with the experience we made for the restriction effect and all the pitfalls, artifacts and problems and background gradients, so it was a bit easier, let's say, to now find good data, to get a good data quality. So for the phantom, the fluid phantom, there is no diffusion anisotropy. We found the flat line as expected, and for brain-wide matter in vivo, we found the W-shaped modulation as expected. So quite nice. So we could see that there is anisotropic diffusion in brain-wide matter. So, but this is of course not surprising. You can also see that with diffusion tensor imaging. So how does it behave in comparison? So just a region of interest in the centrum semi-ovale in white matter. So a region of interest with a high anisotropy FA value. So axons, fibers are expected to be quite parallel. So the conventional DTI experiment shows a significant signal modulation depending on the absolute orientation of the diffusion weightings, whether they are parallel or perpendicular to the fibers. The same holds for the double diffusion encoding experiment. A similar signal modulation is observed for the parallel and for orthogonal combinations, but you can also see that the mean signal for the parallel orientations is well above the mean signal for the orthogonal combinations. So this again is a marker of the U-shaped, W-shaped modulation curve we have seen before. But that's nothing special, that's already in the DTI data. So let's come to the real acid test, let's say, for the double diffusion encoding to show that it can add extra value. So a slightly different region of interest, similar voxels, but we changed the weighting factor. So not just adding up all the voxels, but doing a weighted averaging such that the FA of this region of interest now is exactly 0. So that now we have distribution of axons of fibers that is more or less arbitrary all over the sphere. So this is reflected in the diffusion tensor imaging data, almost a flat line, just a bit noise, and when you calculate the FA, it's really 0. But now, so the diffusion seems to not to be anisotropic. We know it's white matter, it must be anisotropic on a microscopic scale, on the voxel level, on the fiber level, but we can't see it with the DTI experiment, it's invisible to it. So this is where now the double diffusion encoding comes into the play. So you can see also that the signal also does not vary very much anymore, but you can see that the difference between the parallel and the orthogonal directions is still there. And this now proves that the diffusion, even in this RI, is really anisotropic, something the diffusion tensor approach failed. So we can come back to our volunteer who was waiting for the diagnosis for several years, what's going on in his white matter, and having now a look at the double diffusion encoding experiment, you can see that these regions with the reduced FA values, they really behave quite normal like all the other white matter regions. So that means on a microstructural level, everything seems to be fine, and this is just a problem of the crossing fibers. So if you want to apply the experiment, of course, you need to make sure that this, what you get is a reliable measure, that it is rotationally invariant. So we had to do some mathematics, let's say, similar to the diffusion tensor to determine how the microscopic diffusion anisotropy can be mapped in the human brain. We came up with a MA index, which is derived from a quite complex tensor model that's based on ideal timing parameters. It is rotationally invariant, and we found that it requires at least 15 acquisitions at a higher b-value, 3 at an intermediate b-value, and 1 without diffusion weighting. So that's the minimum number, but if you really go to real scanner, it's always a good idea to have a bit more. So including antipodal combination and reversed order direction combinations can improve the data quality considerably, because eddy currents and background gradients and so on are averaged out, and this can be seen for the phantom here, fluid that has no anisotropy. If you just have the simple scheme, let's say here, you can see there's a broad distribution of values, and it's not centered at 0 where it should be for the isotropic phantom, 4 average of 15 direction combinations. But if we go to direction combination scheme with 42 combinations with just 1 average, so less acquisitions than here, we can see it's again centered around 0, and the variability is considerably reduced, although we have less acquisitions. So it's recommendable to use at least 42, but if you really want to have very good data, it would be better to have even 48 plus 12 plus 1. So we ended up with a direction scheme of 96 directions, which we used for the subsequent acquisitions. So we went to young, healthy volunteers, like 20, I think, so, and measured FA and MA in their brains, in their white matter in particular. Not surprising, we have seen that before in the single volunteer. You can see that in their FA maps that there is a significant variation between the different regions, whether they are fiber crossing, the FA is really low, in the pyramidal tracts they have really high values, and you can see that for the MA the values are much more homogeneous. So if you consider 14 regions of interest, we see the values are quite close to each other, so you cannot see here the pyramidal tracts very well, so they are more or less iso-intense compared to all the other white matter we see. The other interesting thing is considering the coefficient of variation across the volunteers. In most of the regions we have investigated, we have found that the coefficient of variation is reduced for the MA. So this may be due to the fact that the crossing of fiber or the fiber orientations within the volunteers may differ quite significantly between the volunteers, and they add extra variability on the FA, where the orientation of the fibers is included, but not on the MA that is supposed to be independent of the orientation of the fibers. So the next step, we did a comparison with aged volunteers, so volunteers with the age of 60 or above. Sorry, John. So, and we were looking at the differences between these two groups. For the FA, so these are now highlighted here. For the FA, for instance, we could see some significant difference in corpus callosum and also somewhere here in frontal white matter. But here in between, where the crossings are, and where you would expect that these fibers that are affected here in the other regions are passing through, you don't see a significant difference. Maybe because the variability between the volunteers is too large because of different fiber orientation distribution. But in the MA, you can see that. You can see that even this region with the fiber crossing now becomes statistically significant. So this means that the MA may be more sensitive to detect changes that are just microstructural of nature and are not depending on the orientation distribution. But I should emphasize that it's not what is better, the information is different. So while the MA really tries to focus on just the microstructural properties, the FA in addition contains the orientation distribution. So that means you can also learn something from when you compare both measures, for instance. So this is a simple example, summary already. So we have the double diffusion encoding that offers additional degrees of freedom, the mixing time, the relative angle between the two diffusion weightings, which requires a quite careful setup to be sure that you do not have artifacts or strange signal modulations. There are characteristic angular signal modulations for restrictions at short mixing times, the bell-shaped modulation and the diffusion anisotropy at long mixing times, so the W-shaped modulation. And these techniques could be used to estimate compartment sizes in the human brain or microscopic microscopic diffusion anisotropy, which is maybe more interesting. So some discussion issues that may be relevant. So the good news is that we have now specific extra information that's coming from a different experiments. It's not just the usual p-value variation, and it contains very specific information about restriction and about microscopic anisotropy. So this may help to improve all the modeling approaches of tissue. We have seen that imperfections, eddy currents, background gradients, and so on play a role, but maybe the good news is that the effect of these imperfections for a simple gradient scheme is easier to oversee. So what's happening, you can easily estimate what could be the effect of background gradients, for instance. Regarding the estimation of compartment sizes, so this effect here, you should be aware that the information is identical to the temporal dependence of the diffusion coefficient, but we heard that also in the talk of Ivana, but it may be more reliable and more easier to detect or to distinguish or to determine these sizes with a double diffusion encoding experiment. And for the microscopic anisotropy, you would expect that the experiment provides really access to the pure microstructure of the tissue without being confounded by the orientation distribution like the FA, but that the comparison with the FA may help to identify what's going on with the tissue, what is lost, and what orientational changes happen in a disease, for instance. The cons, of course, are you need extra scan time if you want to integrate it in your model, and of course SNR, because you have two diffusion ratings, may be an issue. So one of the first conferences I was attending, so I heard the old MRs saying there are two things in life you can't get enough of. One is SNR. So this is particularly true for double diffusion encoding. So with this, I would like to thank all the colleagues that are involved in these studies, in particular Marco Lavrens, Martin Koch, who is now in Lübeck, and Jascha Gödicke. Thanks, Derek, for the invitation, and thank you all for your attention and the discussions we had in the last meeting.
So, question? Any questions? One there.
Thank you. I like these approaches to measure microscopic anisotropy very much. My question is, does it vary depending on the region, or is it more or less nearly the same in the whole white matter?
So when we just have a look at the values, there is some variation, but it's much smaller compared to the FA. Whether this is now really something that has to do with the structure itself, or whether this is an SNR issue, so we're not sure, but I would expect, or my feeling would be, that it's also a little bit different in the microstructure that's underlying these difference of the MA index values.
Okay, thank you.
Thought I saw.
Sorry, you got a question?
No, I thought I saw a hand over there somewhere. Did I see a hand over there for a question? Well, I guess not.
So, thanks, Jürgen. So the point of the microstructural FA is it takes out the variation in orientation. But I was just sitting thinking, what about variation in microstructural anisotropy within the voxel? So you imagine you have your rice grains that are all got different anisotropy.
I think that should be retained. So just what is related to the distribution of the orientation distribution, that should be removed, ideally.
Right. But of course, you only get one number out. You don't get a distribution of micro FA. So is it simply that the impact on the signal is just that you get the average, the voxel average microstructural FA?
So far, yes.
And so if you had uniform micro FA of 0.7 and a distribution, a wide distribution, whose average was 0.7, would the signals look the same in the double diffusion encoded experiment?
That's a good question. No? Some suggestions from the audience.
Yeah.
I guess you may find a distribution where it may look very similar.
You will need multi-shell.
Yeah, no, sure.
I'll show you. It emerges Q to the fourth level, right?
So q to the 4th will probably be the same, right? At q to the 6th, you might see the difference, right?
Yeah, but that's of course quite different, let's say. I think that's what we really see. So the q to the power of 4, that's for the ideal case, let's say, where we really see the full restriction. So that means if you really explore also in the direction of the fibers, the restrictions. But that's not possible. They are too long, so the time is too short. So I think a lot of is just seeing the restriction perpendicular to the fiber and having free diffusion in the other direction. So this is maybe why we can see it quite good. So it's not the ratio of the dimensions, but it's one is really infinite, let's say, and the other is not, the other is small. So that's, yes.
Well, I guess it's time to
Yeah.
go to the next.
Thanks, you.
Okay.